first of all, quick announcement. Maybe you guys have seen this before. There's a colloquium tomorrow called "Why Not Grad School." That's not why you shouldn't go to grad school. That's like, why wouldn't you go to grad school? Okay? I'm actually the colloquium speaker tomorrow, so if you have any interest in grad school, if you think it might be for you, if you'd just like to learn more, come check it out. So that's tomorrow at our usual colloquium time of 11 a.m. Okay, but for reals, what we're talking about today is generative adversarial networks, and continue our discussion about how they work, how we train them, what they can do, why they're useful, etc. I found this funny. This is not an actual XKCD cartoon. This is like some dude. This was like his attempt to represent what might happen if you threw a generative adversarial network at the database of XKCD comics. What would it come up with as a new comic? And I thought it was pretty good because you're like, oh yeah, it looks totally like XKCD, but if you squint, you realize it makes no sense. Just like every other thing that we've seen so far. If you're not an XKCD fan, this maybe not. Okay, so we have no business, so I just want to dive right in and continue our discussion of GANs, and in particular, go back over this. So I know we had gone through it kind of quickly, and we had sort of discussed this, but we hadn't really finished it. And I thought since you guys are going to be implementing this, we should probably cover it and see if there's any questions. I was a little bit like, oh man, I feel like I didn't do a very good job of explaining where this algorithm comes from. So I went back to the paper, and I found some quotes that I think are useful for understanding what's going on. So, if we remember, the basic GAN was set up as this gain theoretic loss function, right? Some expectations and some logs. Some people showed that that is equivalent to a particular divergence between our true data distribution and the data distribution that GAN has learned, called Jensen's Shannon divergence. And they then showed that that's actually not the best choice of divergence, and if you use a divergence instead called the Earth mover divergence, you can derive a new kind of GAN with a different loss function, and that loss function is much better behaved. Okay, stand by. This is saying something funny. Okay. Microsoft PowerPoint is not responding. You have to wait and quit. That was the wrong choice. Okay, so if you replace it with this new divergence called the Earth mover divergence, you get all of these interesting technical benefits for free. But there's this weird technical condition, and the technical condition is that you have this Lipschitz constraint. Okay, so I went back to the paper, and I found this quote that I think, these two quotes that I think kind of explain a little bit better what's going on. I'm just going to read them to you so that I get them right. You can also read along with me. So we now propose an alternative way to enforce the Lipschitz constraint. So remember, we have to somehow ensure that the discriminator satisfies this constraint. A differentiable function is one Lipschitz if and only if it has gradients with norm at most 1 everywhere. So we consider directly constraining the gradient norm of the critic's output with respect to its input. To circumvent tractability issues, we enforce a soft version of the constraint with a penalty on the gradient norm for random samples x hat sampled from this thing x hat. What's x hat? We implicitly define x hat sampling uniformly along straight lines between pairs of points sampled from the data distribution and the generator distribution. So we're sampling somewhere in between that. Remember, that's that epsilon thing. This is motivated by the fact that the graph of the optimal critic consists of straight lines connecting points from the data distribution to the generating distribution. Given that enforcing the unit gradient norm constraint everywhere is intractable, enforcing it only along these straight lines seems sufficient, and experimentally results in good performance. That's going on. Okay.
So didn't we decide last time that we're only enforcing the gradient at one point instead of some line in the gradient space?
Yes. So right, this is like the world's worst approximation. You're supposed to enforce it everywhere. So instead of enforcing it everywhere, we enforce it at exactly 1 point. Yes?
Yes, but isn't this implying that you should enforce it along the line?
Well, that point is sampled across the line. And so
Okay.
over time, because stochastic,
So overall, we're only enforcing one line.
yeah, so it's like there's this distribution over here which represents the data distribution, and this is our current approximation of the data distribution. So this is the true data distribution, this is the generated data distribution. So we're sampling points, and we're drawing lines, and then we're picking epsilons along those lines. And so we're really only, so every time we're picking a different one.
Okay.
So it's sort of like we're stochastically sampling this space in between these two distributions. Over time, as these get closer and closer together, then we'll be picking these points everywhere where the distribution is support. Yes?
I had a shower moment where I'm like, this means that we can't use values, right? Because there's not a second derivative of a value.
Oh, okay, so,
It completely messes up the background, right?
first of all, I feel like I should give you extra credit for that. Like, congratulations for thinking about deep learning in the shower, that is awesome. Good question. So, the question is, if our loss function has, so let's read this line one more time. So the loss function on the ith sample is whatever the critic outputs on the real thing, on the generated thing, minus whatever the critic outputs on the real thing. And there's this lambda term, and then we take the gradient of the discriminator and calculate its norm, and then subtract one. So we're trying to tell how far away is this from this. And so your point is that, hey, wait a second, if this is part of the loss function, we're taking the gradient of the loss, that means we're taking the gradient of the gradient, and that means double gradients are values, and doesn't that
Go to 0.
go to 0 somehow? Doesn't that explode? I think, so I guess I'll answer empirically. Clearly, like, it doesn't explode because it works. So, but it's a good question. Let's see if we can understand it. I think the secret is probably in the fact that this is a detail we glossed over last time. It's true that we're taking side of the gradient of the gradient, but only sort of. This gradient is calculated with respect to the inputs, whereas the outer gradient will be calculated with respect to the parameters of the neural net. And that may be the saving grace. I'm going to have to think about it really hard to know. I'm pretty sure that's why it's okay. Yeah, probably what's going to happen is, as you backprop through this, it's like an extra path through the computation graph, and you're going to ask, how can I minimize the loss? Okay, I can minimize it by changing this. Okay, how can I minimize this? And you're going to ask, how should I have changed the thing that I generated, all right, such that this gradient is closer to unit norm? And that will involve a gradient for, yeah, I don't know. That's interesting. I've never thought about that. I'm not sure. It does seem like you would double differentiate. I don't know. Good question. Really good question. Okay, so how do you feel about implementing this? If you don't feel like you could code it up, ask yourself, why couldn't I code this up? And then ask the question, and we'll see if we can talk about it and figure it out together. Yes?
So you had mentioned that GRUs are really hard to actually get to train. Well, is that referencing, sorry. Is that referencing specifically before this algorithm was discovered, or like
Yes,
even
yes.
with this?
Even with this, they're hard to train. But this makes things better.
Okay, so I still don't feel good about implementing it then. Because you said it's really hard.
It's really hard. It's hard to get going. We're going to try to discuss as many tips and tricks as we can over the course of the next few lectures so that we are all armed with. So, I mean, we've gotten this to work. It's like any of the other labs. It's like if things go well, it works. But there's a million ways that you can foul it up. And we'll try to talk about some of those gotchas as we go along. The next thing we'll talk about, by the way, is we'll also begin a discussion today of the actual architectures of the generators and the discriminators, just so that we have a sense of what they look like. Yes.
I feel like the math would probably be fine, but I'm probably gonna make the like runtime hang somehow.
Okay. I'm sure it'll be fine.
Something's probably gonna get big or like eat all the RAM that I'm not thinking about.
Yeah. Hopefully not. So let's talk about one gotcha really quick that I want to make sure that we're all on board with. When we think about a generative adversarial network, we need to be aware that the discriminator often shows up multiple times. So here's what I mean by that. Notice that in this loss function, forget about the gradient norm penalty for just a second. We're calling the discriminator on the fake data and the real data. Discriminator gets called twice. If you're not careful in your code, you don't want to instantiate two different discriminators. You want to use the same parameters for both of these. So you want to reuse parameters. Because otherwise you'll have a set of fake discriminator parameters and a set of real discriminator parameters. Like nothing will work right. So it's very important that when you instantiate your discriminator class, and you have all the parameters, you call the same object. You can call its forward method multiple times, but you just should only instantiate one of them. Hopefully that's clear. Good. Any questions?
So, kind of like the way I try to like approach these labs is to try to do things kind of like small, like little components.
Yes.
And try to like prove to myself like, okay, I know this little piece is working.
Yes.
Do you have any recommendations for like sanity checks we can run while we're programming these, just to like?
Yeah. So you can start with very simple topologies and very simple data sets, and just try to make sure that they work on really small things first. So like one layer sort of thing. One fully connected layer that just maps the input to the output. Something terrible. And then just see if you can train that at all. And then begin to complexify from there. I think that's one of the best strategies. Then there's some of those other tactics that we talked about. Try to make sure you can overfit on just one sample. Try to make sure that your loss function values make sense as far as the scale. Try to make sure that as you adjust regularization parameters, things go up or down. Yeah.
Cool, thank you.
Yeah.
Okay, so I have a couple questions. The
Okay.
first one is, do we know like when the specs will be complete so we can start working on it? It seems like this lab could use like a little extra time.
Yeah, we should start working on it now. I don't know where the TAs are at on the specs.
Okay.
I will find out. We have a TA meeting tomorrow. I'll ask.
Okay, and then the other question is, so like what kind of classes is this going to involve? Is it like a discriminator class, a generator class?
Yeah.
Is it set up that way?
Yeah, so you're just going to have a generator class and a discriminator class. And then you'll just go, and so those will be pretty straightforward. Those are going to look like ordinary neural nets that you know and love. There'll be some convolutions, maybe some transpose convolutions, maybe a few fully connected layers. Nothing super fancy.
Okay.
The real trickery here is in this training algorithm. And actually, as we go through this, I hope you'll see, it's not that bad in the sense that, so you'll sample a Z, just right from NumPy. You'll pass that through your generator model. So that's just going to be some feed-forward network with a couple convolutions. You'll get an image. This is this is like one line of code. You'll call the discriminator on a couple of images. This is going to be the only tricky bit that you'll have to think about. But then everything else is you just sum up all the losses, pass to Atom, do some batching, do that. So the scaffolding isn't too bad. That's right. Yeah.
So, maybe I just missed this when I went over it, but, so the generator is mapping Z values to, in our case, an image space.
Yes.
Right? And the discriminator is mapping an image space to vector?
1 or 0.
1 or 0.
So it's trying to figure out if it's real or fake.
Okay.
And yeah.
So it's a scale.
It's a scale.
Do we train the discriminator before we start training the generator, trying to get it to generate things, or does that happen simultaneously?
We're training them both simultaneously. So notice in here, there's 2 calls to Atom. So one is training, so let's see if we can figure it out. Which one is this training? with respect to W. What is W? Critic parameters. Right. So W's are critic parameters. Thetas are generator parameters. So in this inner loop, we're training the critic for n-critic steps, where n-critic is some sort of hyperparameter. Then, so for every, let's say it's 4. So we'll take 4 steps. We'll call Adam 4 times to train the critic. And then we'll do a little bit of training on the generator. So we'll go back and forth. Is that clear?
Critic and discriminator are the same thing.
Sorry, yes.
Okay.
The reason, by the way, the math in the Wasserstein-Gann paper, the improved Wasserstein-Gann paper, makes a little bit of a leap that we haven't talked about, which is that ordinarily we think of the discriminator as outputting a number between 0 and 1, and it's like a probability of fakeness. But with the Wasserstein-Gann, it's actually the case that the discriminator can just output any number that it cares about as long as they match. So that's why it's called a critic, because it's slightly different properties. Yeah, so the output doesn't have to be between 0 and 1. It's just like a subtle technical. Okay, any other questions? These are great questions. Yes, keep on.
Is n-critic tunable?
Yes. It's not learnable, but it is tunable. Yep.
I've heard that things train better if your discriminator doesn't learn too quickly. Are there any suggestions for learning rates on these?
Well, the point is, oh, well, okay, so yeah, you're talking about the balance of power.
Yeah.
Yeah. I don't know what the best practices are, to be honest, these days. I'm not sure there's any hard and fast rule. If it seems like your generator isn't making any progress, try training your discriminator less. Yeah, Kyle.
So it looks like here on line 6 that we're mixing one real, like if we're doing image generation, one real image with one fake image.
Yep,
with
that's
certain
right.
random proportion.
Yep.
That's what we do. We don't give it a list of real and fake. We give it like a mix of a real and fake.
Correct. X hat is a mix.
And so then is the generator, or is the discriminator trying to guess the epsilon?
Nope.
Or how?
So epsilon is sampled from a uniform distribution between 0 and 1.
Mhm.
We use epsilon to create this average of these 2 images. So this is, yeah, so X hat is a little bit funny. It's this cross-faded image. And we're only using it to help enforce this gradient norm penalty.
Oh,
It's
okay.
its only purpose.
Yeah.
So notice that's the only place X hat shows up here. That's what I have over here. No? Okay.
So you said the critic parameters aren't trainable?
Not trainable, they're tunable though, you can adjust them. But you don't back prop. Sorry, n-critic. The number of critic steps is not a trainable parameter, it's just some hyperparameter you have to pick. Like 3 or 4. Yeah.
So, back to the discriminator. So it talks about using like a leaky radio as the output layer or output activation for this network.
Mhm.
So ideally we want the discriminator to output a 1 for a real image and a 0 if it's totally fake. But it could hypothetically be any value, any real number, right? How does it know, like where in here are we telling the discriminator that like a 1 for a good image is good and a 0? Does that make sense?
Yeah.
Like
Yeah.
where are we, what here tells the discriminator like what it wants to find?
Yeah, it's this subtraction right here that's the key. I, to be honest, don't know. I've studied the math of this a couple of times, and I wish I had a better sense. It's just this odd thing. You go through the math of the way they set up this earth mover distance, and when you sort of plug it all in, this is the expression that pops out. So it's deeply intertwined with the earth mover distance and what that means. I wish I understood it better.
So it's not
Okay.
obvious,
It's not
but
obvious.
that's what it's
It-
telling you.
Yeah, it's, well, this subtraction is the key right here. Something about real and fake should be the same. What I've never understood about this is why there isn't like an absolute value around this or something like that.
Yeah.
It feels like if you want to minimize this loss, you could just make both of these really negative and just keep going negative, negative, negative. But I guess there's something implicit that says if these are drawn from the same distribution and you're trying to minimize this, then yeah, it just feels like there's like a scale parameter that you can sort of arbitrarily drive negative. And for some reason, that doesn't happen, and I don't understand why.
So it works. And that's all you have to do. Okay, so it's not obvious.
Yeah, I wish I was a better mathematician. Yeah,
Okay, that's fine.
it's not obvious.
Thanks.
But I should learn. I should go try to see if I can figure it out. It's been a while since I've like really dug through the details of the paper, so maybe I'll take a look.
So, can you explain what is inside the assigning to W and omega? Like, what's inside the call to Adam?
Okay, right. So the question is, what's this little expression right here? So let's see if we can parse it out. So this is probably fast and loose notation, but let's see if we can infer what they meant. So we're calling Adam, and we're asking it to take a gradient of something. What are we asking it to take a gradient of? Yeah, some loss function, which is the average of the individual losses. And what are we asking it to take a gradient with respect to?
W.
W.
Which is the
So
parameters of the discriminator.
right. So we're gonna go ahead and calculate the gradient of the overall average loss with respect to the critic. That's gonna give us some gradient. Here are the parameters that we're using, and then we're gonna take whatever Adam gives us and we're gonna update W and call that our new W. That's what they mean by this. So similarly down here, you can see that when it's time to update the generator, we're calculating the gradient, not with respect to W, but with respect to theta of what? Well,
That's like the modified loss function that we saw before.
right?
So are we not including the regularization to like keep our gradient, to bound our gradients in when we take a step on the generator parameters?
Well, right. So the question is, hey, does the gradient norm penalty show up? And it doesn't show up for the generator, and that's because the Lipschitz constraint is only applies to the discriminator. It's part of the again, super deep technical detail. I wish I understood that. Go ahead.
So the kind of, I think there have been similar questions, but would it speed things up at all to kind of seed the critic as like some VGG classifier or something? So if I want to make pictures of cats, I just pull out relevant layers and weights from VGG or something pre-trained? Or would that make it too strong? Or
That's a good question. I don't know. I don't know if people have done that before. It's possible. It seems like that would probably work pretty well. I don't know. And then maybe what you do is not train. So warm start your discriminator with some awesome pre-trained model, then not train it for a while, so let your generator catch up, and then start co-training or something. Yeah, you could probably do something like that. Probably someone has tried that. I'm not aware of it. Okay, and that.
What is the lambda doing there?
Lambda is just some hyperparameter, which is the strength of the gradient norm penalty. 10. It's 10. So remember, this is the way that we're enforcing this very technical condition on the Lipschitz continuity of the function. Instead of enforcing it on the function directly, we're implicitly enforcing it on the function by saying that, this is this observation that if you want the function to be one Lipschitz continuous, that means that its gradients can never be more than 1. The norm of its gradients can never be more than 1. So here, we're just checking if a point has a norm greater than 1, actually, or less than 1, which is another oddity in the paper, but whatever. We go ahead and that's a penalty. So we're trying to learn a function, and I think the reason for this I think must have to do with just making sure that everything is mathematically coherent. So we started with this principle of earth mover divergence, and from there, everything else has come out. So that gives us our loss function and it gives us these conditions. And then that in turn turns into constraints on our, or terms in our loss function. Does that answer your question? Okay, I think we should probably move on. One more question.
Does it have to be the 2 norm always, or the?
I don't know enough about Lipschitz continuity to know, but
That 2 is implying that we should use the 2 norm.
I think, yes, yes. Sorry, that's right. That is the 2 norm. Yes, and that's what you should use. Good. Okay, so then let's, oh yeah, and I showed briefly this slide. I think it was kind of fun to go through and show some of the results. So this is from the Elsun bedroom scene data set. It's a big data set, all the pictures of our bedrooms. And these are generated bedrooms. So it's the usual GAN story of if you look, you look at that one, you're like, wow, that's amazing. And then you look at that one and you feel like you're in some Dr. Seuss house. Where you're not quite sure. But if you squint your eyes, the statistics look about right. So I think it's pretty good. Some pretty good results. Okay, so let's talk about GAN architectures really quickly. So I'll just briefly take you through one of the original GAN architectures for the generator, and just to give you a flavor of what it looks like. This kind of comes from a paper called the DC GAN, which is the deep convolutional generative adversarial network. So this is a great paper because they tried to go through and say, what is it that GAN needs architecturally on the generator and the discriminator side? And they came up with a couple of principles that they thought were helpful for building an architecture. And these are the principles. So first of all, no pooling layers. Only use convolutions. Second, use batch norms. Don't have fully connected hidden layers. Try to use ReLUs except the output where we use tanh, and use leaky ReLUs in the discriminator. So these were not derived mathematically. These are just principles that they thought were useful based on a lot of experimentation. The result is something that is nothing but convolutions. And so for that bedroom scene modeling, this is the original DC GAN architecture, which I think is a pretty good place to start if you're going to build a GAN. So let's go through it and let's figure out kind of what's going on. So remember, this is the generator. So remember, the generator's job is to take as input a vector z and then somehow generate an image from that vector z. And so this is how they do it. So the first thing, so you have some z, which is in this case 100 dimensional. So you take that and you project and reshape and you get this thing. So you go through a couple of convolutions and you reshape it so that it looks like a 4x4 by 1024. Or sorry, there's like a little fully connected layer right here. Fully connected layer that goes from 100 to 4,000, or sorry, 8,192. And then you reshape that thing into this. And then you start doing convolutions and more convolutions until you finally, sorry, these are transposed convolutions, until you finally get to something that is, in this case, 64 by 64 by 3. So an image. Okay, do you think you can code this up? Not too bad?
Can you go over that first step again, from the 100 to the 10?
Yes. Okay, so you start off with a 100-dimensional vector. What you need to do is you need to get it into some reasonable shape so that you can start convolving things. And so the very first thing you do is a fully connected layer right here. And so this block is 1024 filters and a 4x4 image. So that's 8,192 total numbers in that tensor.
16,000.
Oh, thank you. Yes. I lied. 16,000, I'm so sorry. 16,000. So you take this, so how do you get something that's 100 dimensional to be something that's 16,000 dimensional? Fully connected is the answer. So we have some big, some huge matrix, which is 100 by 16K, and when we take that z vector and multiply it through, we'll get a 1 by 16K vector. We then take that vector and reshape it to be 4 by 4 by 1024.
So when he talks about using no fully connected layers,
Except at the beginning.
Except at the beginning. So there's
There's actually one at the beginning. Yes. It has to be one. Okay, yeah. And then, but then there's nothing else. So this is a fully convolutional architecture. Okay, good. Interestingly enough, so this DCGAN was a little bit older, so this is from 2015, and they talk about training. And so sorry, any other questions on this? Do you feel confident? Like maybe you could code this up if you have to. If so, I give you this picture and say, go, you're good? I mean, I think this is pretty trivial now for deep learning ninjas of your caliber. Okay, I thought it was fun to kind of read this paragraph, by the way, from the paper. We won't spend much time on it, but it's just funny to read this. So this is back kind of before people had really coalesced on some good principles for training, but training the mini-batch, stochastic gradient descent, using leaky values. They used Atom, and that was kind of like a big deal because it was only 1 year old at the time. Now, of course, everybody uses Atom. But they talk about all the parameter tuning they did. And then they were able to generate some images, which this is on the same bedroom task. So again, like plausible results. They did one other interesting experiment though that was kind of cool. So remember we talked about z-vector interpolation? So you can do z-vector interpolation in bedroom space if you want. And that's kind of what they've done here. So I think it's kind of fun to look at. So like consider this row. This looks like, I don't know, like some lamp-lit bedroom scene. And then you interpolate, and like all of a sudden this window appears out of nowhere, and you get this fully lit, hotel-looking bedroom scene here. Or this is great here, where this what looks like a picture on the wall kind of turns into a TV, kind of turns into a wall, kind of turns into a curtain. So this is very interesting to kind of think, like, wow, yeah, if you're going to smoothly interpolate in bedroom space, what does that even mean? I actually think this highlights a weakness with GANs, which is that it doesn't make a whole lot of sense to smoothly interpolate between a scene where you have, say, some tables and chairs and a scene where you don't have some tables and chairs. That feels like a discrete kind of thing. And there's actually no smooth interpolation between having chairs and not having chairs. I think there's probably some research to be done in combinatorics, like combinatorial sorts of GANs, where you have a bunch of discrete variables which talk about the presence or absence of things. And they're not necessarily interpolatable, but that's just me. Okay, so let's have some fun now. Just a couple things that I think would be interesting for you to see. First of all, I mentioned this, but there's this really interesting work about text to image synthesis. And they use something called a conditional GAN, which I thought was interesting for us to study and just kind of look at a little bit. So this is from a paper from a couple years ago, a fellow named Scott Reed at the University of Michigan. And the problem is the following. So we mentioned this when we very first started talking about GANs. I'm going to give you some text, like a description of a bird, and you have to generate the image that accompanies that text. And so he's trained this on images of birds and flowers, and I thought it'd be interesting to see how he did this. So here's his architecture on the generator side. So the question you might be thinking is, well, how do you get the text? Like, where does the text go? How does that work as part of the generation? And so this architecture, I hope, makes it clear. So the idea that he had was, well, let's take the input sentence, and we'll go ahead and encode it using some sort of embedding that we've kind of like a sentence embedding, like what we've talked about. We'll then take our z-vector, whatever it is, 100-dimensional z-vector, and we'll concatenate them together. And that will be the input to the generator. Then the generator will go through some sequence of convolutions, kind of like in the DCGAN architecture. That'll give us some image. And then the discriminator will be trained, and it'll actually also have the text. And so we'll go kind of in reverse, where we'll take the image, deconvolve it a bunch of times, and then concatenate the text, and then ask the discriminator to output a 0 or 1. And the reason that they do this, so the reason that they give the discriminator both, so the discriminator has to have the text. Why? Why does the discriminator have to have the text? Yeah.
So see the generated image matches the text.
Right. So the discrimination task here is a little more subtle than just ordinary discrimination. It's not that we're looking for realistic images of birds or flowers. It's like, no, I asked you to generate a flower with yellow petals and like a red stamen or something like that. And so the discriminator has to know that was the task in order for it to be able to tell whether or not the generator did a good job. And this actually shows up in the training where you can sort of mix and match. So now there's lots of ways to generate fake data. So one way to generate fake data is to have an image that's not of a bird or a flower. Another way to generate fake data is to mispair them. So here's a sentence and an image that doesn't go with that sentence. And can the discriminator tell that that's a fake pair?
So is this kind of like an autoencoder, like going from your sentence to an image back to a sentence?
It kind of feels like that, except not quite, because we're not generating the sentence. The sentence here is given, being plugged in.
Gotcha.
But it does, I mean, yeah, if you look at it, it does look kind of like an autoencoder. Okay, and I guess we can play it. I wish we had more time. Okay, we better skip this. I thought it'd be fun to just look at some of these results. So these are, here's the text, and then these are various variants of his GANs. With different kind of regularization stuff. But I just thought it was kind of cool. To me, this was pretty impressive. I thought, oh wow. So, you know, a tiny bird, tiny beak, tarsus and feet, blue crown, blue converts, black cheekbacks. Okay, maybe. This bird is different shades of brown. This is a black bird. This is a gray bird. I was putting in some water here. I think it was impressive to me that it got it right kind of at all. Flowers felt very similar. It was able to pick out the colors of the flower and generate plausible looking flowers, which surprised me. I was surprised that it could do this at all. Okay, we only have a few minutes. Skip that. The last thing I wanted to point out was that if you're embedding your sentences in the same way that you can interpolate in Z space, you can interpolate now in embedded sentence space and plug it into your generator. And what that means is you can interpolate in text space. Which I was like, okay, what's that mean? Well, consider this. So on the left is the image that was generated from this sentence, small blue bird with black wings. And on the right is small yellow bird with black wings. And so those are two sentences. You can imagine embedding those and pick a Z vector. But now instead of interpolating between two Z's, what we're doing is we're interpolating between two sentences while keeping the Z vector constant and plugging that into the generator. And what that allows us to do is sort of smoothly interpolate, I mean, these results aren't super crisp, but smoothly interpolate between semantics of those sentences. So that was kind of a cool side effect of this. Yes?
What interpolation is happening on the right side?
Two randomly sampled noise vectors. Okay, yeah. So over here, it's different. Over here, the sentence is fixed, and we're interpolating between two Z's. So what you should see, so remember, if you plug in different Z's, you should get, ideally, different samples of the same thing that have the same sentence associated with them. So what we should see on the left is a yellow bird with bright blue wings, and on the right, another yellow bird with bright blue wings. And this is just stuff in between, or different birds in between. So yeah, it's a different kind of interpolation, right? Which I think is kind of neat.
So I noticed, like, on a couple of these, on the right images especially, and on the previous slide,
Yeah.
it almost looks like there's a style of, it's like grainy or like similar to a style of a painting.
Mhm.
Is that like intentional, or
No.
is
No.
that just?
No, so this work was done maybe 3 years ago, back before they knew how to do really good generators. And so it would be really cool to try this work again, but with, for example, some of the techniques that NVIDIA used to generate those really nice, high-quality facial images. Like, people have learned a few subtle things, like don't use max pooling, only use tunable transpose convolutions, things like that. That can give you better images. Also, also, the NVIDIA stuff was trained progressively. So you start by generating small images and then gradually generate higher and higher resolution. This guy didn't do that because they didn't know how to do that back then. Yeah, it's too long ago. Okay, finally, I thought it would be fun to show you this. So we've got just a few minutes left. Introspective adversarial networks. This is a slightly different version. I don't want to go through the details of this method, but they use it in a really interesting way that I thought you might appreciate. So this is a little video all about neural photo editing. So let's get it going, and I think you'll get the idea pretty quickly. Again, this is just like a fun application of this. Let's see.
Photos usually involves some form of manipulating individual pixels. If we have a sufficiently powerful model of an image, however, we can modify that image directly by changing the model's parameters. The neural photo editor is an interface that takes advantage of the modeling power of generative neural networks to allow users to make large semantic changes with ease.